really large room. This is a larger room than we've had for any of the carry-ons before. So mic running is going to be a little bit difficult. So if you have questions for the end of the session, you should line up at the center mic, and that will work a little bit better than having student volunteers run the mic around. Okay? All right. So take us away.
All right, thanks. Can you guys hear me? Yeah. All right. So my name is Avik Chaudhuri. I work at Facebook. I joined Facebook around 4 years back, and that's when we started this project called Flow. It's been around for a while. Today, I'm going to talk about where we're going in the future. So what's Flow? Flow is a static type checker for JavaScript. We've been using it at Facebook for the past 3 years or so. It's fairly widely used. We have lots of JavaScript at Facebook running into millions of lines of code, and it's all new JavaScript code is written in Flow at Facebook, and most legacy code is also being covered by Flow. So at this point, we are at around 70% coverage of the code base, and we are doing pretty well there. It's also open source. It's not the only type checker for JavaScript that you can use. There's also TypeScript. That's pretty popular outside. TypeScript has been designed mostly to aid productivity through an IDE. Flow, I would argue, is more technically interesting. It's not blatantly unsound, for example, like TypeScript is. It's more principled. On the other hand, it's not as polished. So some number of developers choose to go with TypeScript. At Facebook, what we value is catching as many bugs as possible without necessarily adding annotations everywhere that is needed. So Flow works pretty well for that use case. It has a lot of type inference built in. So usually I've given, when I've given a talk on Flow, I've described how Flow works internally, both in terms of the type system and how we scale it to Facebook's needs. This talk is going to be slightly different. We're going to talk about the future. So even though Flow has been scaling at Facebook pretty well, I'm going to talk through some of the scalability challenges that we're facing as our code bases are exploding in size. I'm also going to talk about soundness, which is something that Flow has always been very, soundness has been very important for Flow from the beginning, but we have not really started exploiting it. It's still an optionally typed system where we apply sound inference rules, but you can also have uncovered code that I just mentioned. So I'm going to go into more detail there. So before we start, let's begin with some code, just to give you a flavor of how Flow works. I'm not going to go into too much detail, but this is necessary to understand what I mean by scalability. So this is a simple function that takes a parameter and doubles it, and we call it with a number, and we try to access its length property, or call length method on it. So the way Flow works is it translates this program to a bunch of constraints, um, and the constraints describe what the behavior of the program is. It's very abstract. It's at the level of types, but it still captures very faithfully what the set of values that might flow through every part of the program is. So here n describes the type of small n, which is unknown at this point. But what we know is that it's being used as a number when we are trying to multiply it by 2. Um, the result of that multiplication is going to be a number, and that flows to, let's say, this thing called d, which stands for double, which is the return value of the function. Um, this whole thing that is describes the function itself can be described as with a function type that goes from n to d, and that flows to the type of foo. Meanwhile, foo is being used at a call with passing in the argument, which is a number. The result type is unknown, which is the type of the expression that surrounds foo42. And then we are calling the length method on it, which can also be described as a constraint like this, and the result of the length call is unknown. Right, so this basically gives you a flavor of how Flow translates a program. a JavaScript program into a bunch of constraints, and then it can solve it using very standard techniques, where it applies these rules and transitively closes the rules. So by applying those two, by combining those two rules, you get that the function type goes to this kind of call constraint. Um, and because we know from subtyping how the flows should work, the argument goes to the parameter in a kind of contravariant direction, and the return goes to the result. So we have two new constraints, and then we keep combining these constraints over and over again, and eventually we hit a constraint like that, which says that we are trying to call the length method on a number, and this is an error. So this gives you a flavor of how catches errors in programs. Of course, in JavaScript, not everything is a huge file with a bunch of code in it, and you don't typically stick all of that code into your web page. Otherwise, the web page loads really slowly. So you break everything into modules, and typically these modules are very small to keep the dependencies very fine. Um, so here I've shown you how I split the program that I just showed you, where the function is defined in one file and it's exported, and we import the function from a different file. And the constraints that we generate are more or less exactly the same, except that they're generated in two different files. And the way they are connected is that this foo goes to this thing called E, which is, let's say, describes the exports of file 1, and I describes the imports of file 2. So we add a constraint that says that, well, E flows to I, the exports flow to the imports, and then we can do whatever we already did in the previous slide. So, I said I'm going to talk about scalability, right? So the thing is, this algorithm that I described is an order nk algorithm where k is not 1. K is greater than 1. K is not too large. It falls somewhere between 1 and 3. Typically, the kind of analysis that I showed you is so-called subset based inference, and it's cubic. Um, on the other hand, if we chose to use unification, it's kind of quasi-linear. What we do is a combination of both. We have mostly subset-based inference. However, because some of the subtyping rules that we apply are invariant, so essentially they're talking about equalities and not inequalities, we can use some unification as well. But it's still not one, right? And we'll see how that could be a problem very soon. So N is, for one of our largest code bases, it's already 10 million lines of code and growing very fast. I'll show you a graph later on in the talk to show you exactly how this amount of code is increasing. So if we dive deeper into what N is more or less some constant which describes the maximum size of a file. And typically, this is something in JavaScript that kind of probably promotes this style of programming. But files are individually not that big, and we kind of exploit that fact. Each file is more or less something around 100 to 200 lines of code. There will be the occasional outlier that's some kind of generated JavaScript file. There will be 10,000 lines of code, but mostly it's around this number. And then the remaining number is the number of files that we have in our code base, right? So essentially, this is order of f to the k, where f is the number of files in the code base. So it's essentially order fuck because f is pretty huge. All right, so um, the first thing we do, which we did right off the bat, right? So we kind of discovered right when we were getting started that a whole program analysis is not going to work. So we broke this thing into chunks and did a modular analysis, and annotations were the things that came to our rescue. So what we decided is that we are going to ask for annotations on your exports, and that gives us, instead of f to the k, it gives us more or less f multiplied by some constant, some large constant, but still constant, more or less. So if c is again the number of lines in a typical file, and s is the size of the type of exports, which is kind of order of the same kind of lines of files. It's a bit more, it can be a bit larger, but it can still be bounded by a reasonable number. So we have an analysis that is not f to the k, it's grows linearly with the size of the number of files. And that worked well for us for a while. Today I'm going to describe why even that is not going to work for us in the future. So the way Flow does this analysis in more detail is that it has a dependency graph between all the files. This graph can be pretty large, but we also have a lot of power in our machines nowadays. A lot of developers at Facebook who are developing on the website, for example, they use pretty powerful dev servers with a lot of parallelism. A lot of people also code on laptops, and even laptops have around 8 processors or more nowadays. So we use all of that. Sometimes laptops catch on fire while they're running Flow, but even then, we have that parallelism to exploit. And the way we do this is as follows. We have typically more files to process, many more files to process than processors. So we assign a bunch of files to the processors, and these get started with kind of the leaf files, which don't depend on anything else. And then there is some queue of files that are waiting to be scheduled. And these are files that don't have any dependency. They're just blocked because there are no processors on which they can be processed. And the rest of the files are still live in the dependency graph, right? So at some point, one of those files gets done, and then we inspect the dependency graph, and we discover that some number of other files were blocked on this file being processed. Some of the files that are blocked might have other dependencies that are still churning, so they are out of luck. But for example, the file on the right, um, this file that got done was its last dependency. So it's no longer blocked. It becomes blue. It's added to the queue. We also get some more files off the queue, and then we assign them to these processors. So the way this execution works is it picks some sort of topological sort at runtime, depending on what the load on these processors are. Typically, the processors are always fully utilized because there are a lot more files than processors, and even if some files are blocked on other files can make progress. So this kind of works really well. Um, so the architecture here is that we take a bunch of files and we spend a lot of time analyzing all of the files, and then we call that the initialization phase. And at the end of it, we know everything about the code base, typing wise, and then we wait for other files to be touched, and then we recheck them on demand. Um, so suppose that we touch a file somewhere in the middle, um, and we want to recheck some number of files, at least that one, but potentially other files that depend on these files as well. So we'll end up rechecking a bunch of files. If you touch a file that is very high up in the dependency graph, then this might take some time. But still, it's far less than the number of files that were initially in your code base. So this can be bounded by a few seconds at worst. Um, so, um, but that was, at some point that stopped scaling as well, because people were building huge inheritance hierarchies, for example, or they had long chains of dependencies in the graph, abstraction over abstraction over abstraction. Sometimes these rechecks took really long. So you can't just mark uh, the dependent files for rechecking, because the set of files that you end up rechecking every time you touch a file can become really large very soon. So then the next idea is that we started hashing and comparing the types of exports of a file, and if those exports did not change, then we cut the rechecks. This is also a very reasonable, very simple idea, but the exact mechanics of how this hash function works is a little tricky. I wouldn't say it's too tricky. At the least, you have to make sure that the hash is not sensitive to irrelevant, fresh IDs or variables that you might be creating. But beyond that, yeah, this kind of, if you're really lucky, you will stop right at at the first step. Let's say you kind of add a character or two. Typically, you're not changing the type of your exports, and your dependents don't need to be rechecked. Sometimes you are less lucky. You might end up actually substantially changing something. You add a line and your exports go down one line. Even that might cause you to recheck some number of files because we care about, because of error reporting, we care about locations of where things reside because we want to point back blame to correct locations. So you might end up rechecking some number of files, but you tend to stabilize after a few levels. So this optimization works. This was implemented sometime in end of last year, I think. Um, However, the big problem is this. Even though all of this works at the rate of sort of files that you have in your code base, that number is increasing exponentially. So when we got started around uh, 4 years or 3 years back, we had around 10,000 files that we had to check. In 3 years, we now have 100,000 files, right? So the 10 million lines of code divided by 100 is around 100,000 files and more, right? Every time I look at the number of files, it keeps growing. So that kind of corresponds to this kind of curve, which is really exponential. We are hiring a lot of people. They're writing a bunch of code. So scaling linearly does not work as well. So at some point, a lot of people in the company had this aha moment that our tool should scale not with the size of the repositories, but the size of the working set of an individual developer, which is far more constant, right? So even though we hire a bunch of people and they might be working on different products, and even though we might be using a monorepo with all of their projects in one repository, um, typically the number of files that a particular developer might be touching in any given week is not that large. Even if you count all of his dependencies and dependents, it's not uh, a large number. So we want to scale with that rate. Otherwise, the productivity of each individual engineer is going to halve every year or so, which is not good. Um, so how do we do this? Well, um, the actual implementation of what we do is not very difficult. We just become completely lazy and don't do anything to begin with. So remember I told you about this initialization phase where we look at all the files and we try to understand what all of them do before we start waiting for files to be touched and then rechecked. Uh, Now, as of a week back, in our very last release, we kind of uh, released experimental support for a so-called lazy mode of type checking, which does nothing at the beginning. And then now, when you touch a file, there's a, there's a point at which actual type checking starts. There's not a recheck, there's a check for the first time. So not only do we have to check its dependents, but also its dependencies. So the purple ones are the things that are required for this file to be checked even for the first time. So that's what this involves. However, given that we have a huge number of files, um, at any given point, if you start by doing nothing, and then slowly add to your world as you touch different files, you bring their dependencies into your world and type check them. That number per our measurements does not grow very quickly. It kind of stabilizes after a point, um, and we kind of achieve that kind of sublinear, pretty constant looking scaling factor. So we're kind of excited about this. We'll see how this goes for another year or so. Maybe next time I give a talk, I have to talk about yet something else that we have to do for scalability. So let's switch gears a little bit and talk about the next thing, which is soundness. All right, and here I want to give you some context, which is our website says that Flow is a static type checker for JavaScript, and that's how we tend to market ourselves. But when we designed Flow, it was already clear to us that it's not just a type checker. The real picture of what Flow does is more or less like this. It's a huge box full of gears. There are lots of static analysis going on with one goal in mind, which is type checking. But it's like proving a theorem, right? So often you end up proving a theorem, but prove a really big lemma before you can get to the theorem. And the theorem is just combining some building blocks. But you end up doing a lot more work to carry along the necessary invariants around. So we have some points to analysis built in inside. We have some alias analysis built in. All of these are necessary for Flow because JavaScript is a tiny bit complicated, and we have to support a lot of idioms that JavaScript has. However, what comes out at the end is just this innocuous looking message, which says most of the time it says no errors. Sometimes it gives you a bunch of errors. So you might think that nothing much is happening inside Flow. So one of the aha moments we had at some point when people um, started complaining about, okay, why does Flow behave in this manner, and why is Flow kind of burning my laptop? Um, we kind of poked some holes in this box, and they became really happy. And this is what TypeScript as well does. It kind of exposes more of the gearbox, if you will. So now programmers, even though they may not have any errors in their code base, they are getting some information out of the type system, right? So they can say they can discover what the type of a particular expression is, or a particular method call is. They might want to know which definitions a particular reference is pointing to, a whole bunch of other information that we can expose through an ID. All right, so this was what we did maybe a couple of years back, and that kind of really turned around the perception of Flow inside the company. But why stop here? It had been a dream all along to kind of expose more of this this box of gears, and kind of try to exploit all of that information that Flow has for even more things. Things like transforming your program automatically for performance optimizations and whatnot. So this is what we want to do in the future, and we have started some work in this area. We want to do things like constant inlining and property renaming, things that are more in the compiler territory, more in the territory of transforming JavaScript programs and to equivalent JavaScript programs that potentially load faster, are better in different ways. Um, so you might think that these optimizations are really kind of simple, and they may not get you much, but in JavaScript they do matter. So for example, what is constant aligning? Well, we have a bunch of files that define a bunch of constants. These are typically these represent actions that a particular part of your product might make. We have a bunch of enum-like situations. We have a bunch of strings that define cases in a kind of a disjoint union type, something like what you would do if you were writing an algebraic data type in ML, and you kind of switch on structures of these kinds. So we have lots of constants in our code base, and they're defined in these huge files, and sometimes when they're used, the entire file that defines these huge bag of constants has to be loaded in before that particular code that is using one or two of these constants can be executed, right? So in JavaScript, this is a big deal because you tend, loading huge modules takes up a lot of time, parsing time to begin with, but also other things. So if you inline the constants, it means that you cut those dependency edges, so you don't have to load these huge files at runtime, and you get the same behavior, right? So this is not very hard for Flow to do because Flow already has a concept of singleton types. So a string literal or number literal has exactly that type, and we already use it to check these patterns that people write at Facebook. So constant lining is not a big deal because it's just a type that we propagate from one place to another place. Property renaming is another big deal. So you might have heard that JavaScript gets minified before it gets shipped on your browser or wherever else. Um, this minification process is a process by which code is, so variables get renamed, for example, to shorter names. You might, for software engineering purposes, you might have really long names in your code base, and that's good. But if they can be transformed automatically into short names like A and B and C, then that just means less bytes to ship over the web. Um, if you have to rename variables, that's really simple. A lot of minifiers do that. If you have to rename properties of objects, that's much harder because you need to track where objects flow throughout your code base, and you have to rename their properties in sync everywhere. Otherwise, your code is going to break. So that requires some sort of like flow analysis, the kind of analysis that Flow is good at. Um, so the point is that there's a lot of information in there, and we want to expose these things and become more of a compiler to drive performance optimizations in the future. So this is all well and good. It seems like Flow has the power to do this, but there's a big problem with this. I told you at the beginning that um, Flow also is optionally typed. So at the least, it involves this type called any, which is a dynamic type through which you can interact. And so the question is, which types in your code base can you really trust? So this is a really big elephant in the room. A lot of people who talk about Flow's potential in kind of entering the compiler space are really worried about this problem. And my typical response to that is that it's not a big elephant that we have to deal with. It's really more of a chicken. It's hard to catch chicken, but it's really harmless. And I'm going to use this word called soundy, which some of the people here in the room kind of invented. I would like to see that term formalized because I think there's something there. So Flow was designed to be soundy in the same sense as this manifesto that I'm mentioning described it to be, which is it's mostly sound. Unsoundness is limited to corners. They're really there for a reason, and you can kind of try to segregate those unsound parts. So the plan for Flow in this area is that, well, there's also a bunch of bugs that we didn't pay a lot of attention to because all we had was the ID use case up to this point. But that's fine. We can fix those. Then we add this thing called trusted types, and the main thing here is that we do not want to make Flow to make a different kind of Flow that is a stricter mode of Flow. No, we don't want to do that. We want to evolve Flow to this mode by default, and then we can take advantage of all the checking that we already do in our code base and not have to retype check everything and have yet another set of rules that people have to abide by. This is an important point because some people from Microsoft research had tried to make TypeScript safe by proposing something called safe TypeScript that essentially takes the set of rules that TypeScript has and throws them away and then replaces them by kind of new rules, fixing a lot of the unsounded rules. We do not plan to do that. We basically want to take the same rules and attach some additional information that will allow us to know which types you can trust and which types you cannot trust. Let me touch on bugs for a little while. There are lots of known bugs in Flow, which we plan to fix, but there's a long tail of unknown bugs, and we are kind of really worried about these bugs. And I do not know what the correct solution is to find unknown bugs in a really large production system, other than these things, which is like really stare at the rules hard. Uh, we have some ideas on how to do random test generation to find more bugs. And there's an intern who's doing some good work here. So maybe something will come up. He's actually managed to find some of the bugs we already know about. Um, if we keep managed to not find unknown bugs, maybe there are no unknown bugs. I don't know. We're also trying to formalize various parts of the code base, various parts of the rules, and maybe we'll catch some bugs from there. But the thing that I want to focus on is this idea of trusted types. So typically when people talk about gradual type systems, not optional type systems, but gradual type systems where anything that interacts with dynamic type code has to actually add runtime checks to kind of assert that these types are sound. Um, we are not there yet. And I claim that we can kind of segregate the problem and first try to mark types as trusted and untrusted before we get to the point where we are actually changing program behavior and inserting runtime checks and so on. So the picture is as follows. You have untyped code, and types flow from there to code that is covered. Um, so the really untrusted parts are red. Uh, the things that look like types but are still untrusted are orange. And actually, people already write dynamic checks, and Flow has enough power to refine types based on dynamic checks. So it can recognize after these runtime checks. For example, if you check that something is actually a number at runtime by checking the tag of value, we can promote an untrusted value to a trusted type. So briefly, the rules that we are thinking of look like follows. So in an optional type system, any is the main source of unsoundness because all types are subtypes of any, and any is a subtype of any other type, which is very easily exploitable. So what we want to do is like color the rules a little bit with trusted and untrusted. So trusted or untrusted things can go to any, no problem, at least for primitives. Um, but on the other hand, any can be considered to be a number only if that number is marked as untrusted. Um, for functions and objects, things are slightly more complicated because imagine that you have written a function and it escapes to untyped code. You actually do not know what whether the parameter parameter type can be trusted because untyped code can call your function with arbitrary arguments. But the rule kind of that we were thinking of function types is kind of captures this in a very elegant form. So if you have a function type that is escaping to any, all you do is do what other gradual type systems also do, which is treat any as the function type any to any, and then you have your normal subtyping rules that kick in and try to mark your parameter types as untrusted, which is exactly what we want in this scenario. Same on the other direction. This is just pure typing going on. For objects, then we can extend the same idea. It looks like this kind of tainting is sensitive to polarities, so we can just apply the right rules when we have objects. If we have read-only properties or write-only properties or read-write properties, we kind of do the tainting in the proper directions, and they should work out. However, this is not that simple. With objects, you also typically have a with subtyping rule that allows you to lose some information. This is the basis of abstraction in a lot of languages. So if you have an object with an x property and a y property of different types, you can forget that it had a particular property. So you can cast it to this smaller type, which is x colon t, and now you've forgotten that you had a y property. However, if you leak this object to untyped code, the untyped code can do anything with this object. In particular, it can actually muck with your y. You can overwrite your y property, and then this invariant that y is type of s is in danger. So it should really be marked as untrusted. So just applying these rules blindly is not going to work. So it's still a bit tricky, and we have some ideas on how this can be solved, but it's still work in progress. I did not claim that I have all the answers here today. I wanted to talk about challenges, and here I am, right? So this is done. This is my last slide. I just wanted to summarize that. This is really, I consider this to be kind of chapter two in Flow's lifetime. Up to now, we have been proving that we capture a lot of common JavaScript idioms. We are fairly precise. We scale pretty well. However, for Facebook's unique needs, we need to do some really cool things to kind of scale much faster, and just delivered on that. Uh, but soundness is where we want to go in the future. So in 6 months or so, we hope to make more progress here. That's it. Thanks.
So we have a little time for some questions. Again, just because of the size of the room, if you could step to the center mic, that would be really great. Just to-
Oh, I think I managed to do it. So I actually have two questions, but I started with one. Maybe a lot of people want to ask you something. So what's your plan on moving on with type systems? Like what features are you considering to add? Do you consider to add some features to the type system to make it more expressiveness, like GADDs or maybe dependent, please type something and so on?
Okay, so we actually don't plan to add a lot of features. We consider like the design is mostly stabilized. However, it's easy to add features, and people keep asking for features all the time. So, what we typically do is look at what patterns are emerging, new patterns are emerging in our code base, or from outside from GitHub, and then we try to like respond to those things. So one of the things that we are working on now is this ES7 feature, which is like a feature that's going to come in next year probably, but we already started using it in Facebook, which is object spreads, which allows you to take an object, like spread it into another object. This is very good for like object composition and kind of moves you in the opposite direction as inheritance. So we consider that as a good thing. Um, so we kind of are trying to support that. Um, and a lot of people also ask about some kind of weird kind of types which are more higher kinded types. The idea here is that we have a lot of frameworks which take particular shapes of objects and then transform them to other shapes of objects, and they transform them in a very regular way. So they need types to kind of express these things, these kind of transformations, and they take types to other types. So we have some support for that, and more support is planned because some people are writing some new frameworks that will exploit those things. But yeah, all of these are kind of directed to use cases and not really. So if we don't find a use case, a very common use case where GADTs will be useful, then we'll probably not add GADTs.
And if I may, the second question, it seems that sufficiently typed JavaScript program, flow typed, can be compiled to some more bare metal thing like, I don't know, maybe not like native code, but something like that,
Yeah.
or some other language, because now it's trends to compile everything to JavaScript, but
Yeah.
sometimes it seems like it's a good idea to compile JavaScript to something.
Yes.
Do you like Flow seems to be a good fit for such tasks? Do you plan on doing something or maybe
Sure.
some?
One step at a time. Like let's try to think what trusted types will look like and experiment with a few less ambitious things. But Andreas Rosberg was just here pitching his talk at PLDI, where they are talking about WebAssembly, and it's quite conceivable that one day flow type JavaScript can be compiled to WebAssembly and run much faster than JavaScript. Sure. Yeah.
Thanks.
Hey, Sebastian Erdwig from the Technical University of Darmstadt. I have a question about the scalability section of your talk. So you presented this approach where you use laziness to only check parts of recheck parts of the files. But how long do you do it? Like until you reach a transitive closure where everything that's reachable has been rechecked, or
So no, so that's the whole point of it, because the reason we are being lazy is that one particular developer, uh, given the lifetime of the server might crash for different reasons, but typically a particular developer keeps the server alive maybe for 1 week or so, and in that week he will touch only a subset of files, and it's enough to just type check that subset of files, including its dependencies and dependents. Now, the key assumption that didn't say is that you need to start from a state where there are no errors,
right?
and we already have that built in. So every commit that is checked into our trunk is flow clean. So which means that we can start off from an arbitrary commit after the programmer rebases is kind of local work on a particular commit. We can assume that that commit has no errors, and then we can just look at the files that were touched after that. And if that turns out to be no errors, then it's easy to see why it's safe to check in that code.
And you only look at the immediate dependencies and dependents?
Yeah, immediate, actually transitive.
Transitive,
Yeah,
so.
because there's some amount of inference going on that goes through annotations, so sometimes you have to look at, yeah.
Thanks.
Okay, let's thank the speaker. Really large room. This is a larger room than we've had for any of the carry-ons before. So mic running is going to be a little bit difficult. So if you have questions for the end of the session, you should line up at the center mic, and that will work a little bit better than having student volunteers run the mic around. Okay? All right. So take us away.
All right, thanks. Can you guys hear me? Yeah. All right. So my name is Avik Chaudhuri. I work at Facebook. I joined Facebook around 4 years back, and that's when we started this project called Flow. It's been around for a while. Today, I'm going to talk about where we're going in the future. So what's Flow? Flow is a static type checker for JavaScript. We've been using it at Facebook for the past 3 years or so. It's fairly widely used. We have lots of JavaScript at Facebook running into millions of lines of code, and it's all new JavaScript code is written in Flow at Facebook, and most legacy code is also being covered by Flow. So at this point, we are at around 70% coverage of the code base, and we are doing pretty well there. It's also open source. It's not the only type checker for JavaScript that you can use. There's also TypeScript. That's pretty popular outside. TypeScript has been designed mostly to aid productivity through an IDE. Flow, I would argue, is more technically interesting. It's not blatantly unsound, for example, like TypeScript is. It's more principled. On the other hand, it's not as polished. So some number of developers choose to go with TypeScript. At Facebook, what we value is catching as many bugs as possible without necessarily adding annotations everywhere that is needed. So Flow works pretty well for that use case. It has a lot of type inference built in. So usually I've given, when I've given a talk on Flow, I've described how Flow works internally, both in terms of the type system and how we scale it to Facebook's needs. This talk is going to be slightly different. We're going to talk about the future. So even though Flow has been scaling at Facebook pretty well, I'm going to talk through some of the scalability challenges that we're facing as our code bases are exploding in size. I'm also going to talk about soundness, which is something that Flow has always been very soundness has been very important for Flow from the beginning, but we have not really started exploiting it. It's still an optionally typed system where we apply sound inference rules, but you can also have uncovered code that I just mentioned. So I'm going to go into more detail there. So before we start, let's begin with some code, just to give you a flavor of how Flow works. I'm not going to go into too much detail, but this is necessary to understand what I mean by scalability. So this is a simple function that takes a parameter and doubles it, and we call it with a number, and we try to access its length property, or call length method on it. So the way Flow works is it translates this program to a bunch of constraints, um, and the constraints describe what the behavior of the program is. Is very abstract. It's at the level of types, but it still captures very faithfully what the set of values that might flow through every part of the program is. So here n describes the type of small n, which is unknown at this point. But what we know is that it's being used as a number when we are trying to multiply it by 2. Um, the result of that multiplication is going to be a number, and that flows to, let's say, this thing called d, which stands for double, which is the return value of the function. Um, this whole thing that is describes the function itself can be described as with a function type that goes from n to d, and that flows to the type of foo. Meanwhile, foo is being used as at a call with passing in the argument, which is a number. The result type is unknown, which is the type of the expression that surrounds foo42. And then we are calling the length method on it, which can also be described as a constraint like this, and the result of the length call is unknown. Right, so this basically gives you a flavor of how Flow translates a program, a JavaScript program, into a bunch of constraints. And then it can solve it using very standard techniques, where it applies these rules and transitively closes the rules. So by applying those two, by combining those two rules, you get that the function type goes to this kind of call constraint. Um, and because we know from subtyping how the flows should work, the argument goes to the parameter in a kind of contravariant direction, and the return goes to the result. So we have two new constraints, and then we keep combining these constraints over and over again, and eventually we hit a constraint like that, which says that we are trying to call the length method on a number, and this is an error. So this gives you a flavor of how Flow catches errors in programs. Of course, in JavaScript, not everything is a huge file with a bunch of code in it, and you don't typically stick all of that code into your web page. Otherwise, the web page loads really slowly. So you break everything into modules, and typically these modules are very small to keep the dependencies very fine. Um, so here I've shown you how I split the program that I just showed you, where the function is defined in one file and it's exported, and we import the function from a different file. And the constraints that we generate are more or less exactly the same, except that they're generated in two different files. And the way they are connected is that this foo goes to this thing called E, which is, let's say, describes the exports of file 1, and I describes the imports of file 2. So we add